Chapter 11: Electronics. Now, the functioning of electronic components such as the diode and integrated circuits is based on the behavior of certain materials called semiconductors. Common examples of semiconductors are silicon and germanium. The electrical conductors, semiconductors, and insulators can be explained using the energy band theory. An atom consists of a central nucleus containing positively charged protons and neutrons, which are electrically neutral. The nucleus is surrounded by negatively charged electrons orbiting in layers or shells. Electrons in the inner orbits have least energy and are tightly bound to their orbits due to nuclear attraction. Electrons in the outermost shell experience weaker binding force and can break from their orbits to become free electrons, which can move within the material under the influence of an EMF. The shells are identified by letters of the alphabet, beginning with K for the innermost, then L, and so forth. Each shell represents a certain energy level and have a maximum number of electrons it can hold. According to the energy band theory, when two or more atoms are brought closer to each other, the energy levels split into smaller energy levels called bands. The outermost energy level splits more easily into many bands than the inner levels. The splitting of the energy levels into bands and the gap between the bands dictate the properties of a given material and can be used to distinguish between insulators, conductors, and semiconductors. A band which is occupied by valence electrons and having high energy is called the valence band. The electrons are used in bond formation. The valence band may be partially or completely filled. It can never be empty. In certain materials, the valence electrons are loosely attached to the nucleus. Even at room temperature, some of the electrons can leave the valence band. These are called free electrons. They are responsible for conduction of current in a conductor and are hence called conductor electrons. The band occupied by these electrons is called the conduction band. This band may be empty or partially filled. The separation between the conduction and valence band is called the forbidden energy gap. If an electron is to be transferred from a valence to a conduction band, external energy is required, which is equal to the forbidden energy. Conductors are materials that allow current to pass easily. Insulators are materials that prevent electric flow. Semiconductors exhibit both conducting and insulating properties. Using the energy band theory, we can visualize why these materials behave as such. In conductors, the conduction and valence bands overlap, and thus the conduction band is occupied by many electrons, making them good conductors of electricity. In insulators, the conduction and valence bands are separated by a wide forbidden gap. For an insulator, the valence band is completely filled by electrons, which are tightly bound to the atoms, but the conduction band is empty. The two bands are separated by a very wide forbidden gap, so the electrons are unable to gain enough energy to jump from the valence band to the conduction band. In semiconductors, the valence and conduction bands are also separated by a forbidden gap, but for the semiconductors, the gap is narrower compared to the insulators. This enables some electrons with enough energy to jump from the valence band to the conduction band fairly easily. At low temperature, the semiconductor behaves like an insulator, since there is no free electrons in the conduction band. At high temperature, electrons excited by heat can gain enough energy to jump from the valence band to the conduction band. When this happens, the electrons leave holes in the valence band which behave like positive charge carriers and can also move freely. When a potential difference is connected to the semiconductor, the holes and the electrons move in opposite directions and are called the charge carriers. Let us see how that happens in their real structures. The two common semiconductors are silicon and germanium. They have 4 electrons in their outermost energy shell. In their structure, each atom forms 4 covalent bonds with 4 other atoms. So all the valence electrons are utilized and are contained in the valence band. There are no free electrons in the conduction band at low temperature. This is a better model of the crystal lattice of either silicon or germanium. You can see the valence electrons in the covalent band and no free electrons in the conduction band. How do holes and electrons come about? Although the covalent bond is strong, it's nonetheless imperfect. Therefore, if some heat is applied, some electrons will gain sufficient energy and break from the bond zone to become free and available charge carriers. Whenever this happens, a space is left behind, and this space is the hole. Because the electron is negatively charged, the hole is associated with a positive charge. So it will break the covalent bond, sending the electrons from the valence band into the conduction band. This leaves in its place a hole, which is associated with a positive charge. An electron in the nearby may be attracted to the hole and leaves a hole behind. This way, the hole seems to have moved in the neighboring atom. This process continues on and on as more electrons are dislodged. The electron-hole movement is random, but if an electric field is applied, the electrons fill the holes so that the holes move in the direction of current while the electrons move in the opposite direction. And that is how semiconductors conduct electricity. Because electrons are dislodged by heat energy, more electron-hole pairs are formed as heat energy is increased. This explains why semiconductors conduct better at high temperatures due to generation of more mobile charge carriers, electrons and holes. Also, notice that the atoms are fixed in the crystal lattice and do not move. Intrinsic and extrinsic semiconductors. Keep in mind that in a pure semiconductor like silicon and germanium, every time an electron is dislodged, a hole is created. So at any given point in time, the number of electrons equal to the number of holes. An intrinsic semiconductor is a pure form of a semiconductor like silicon or germanium. Small quantities of impurities may be added to an intrinsic semiconductor to enhance conductivity. This is called doping, and the resulting semiconductor is called extrinsic. Extrinsic semiconductors are further subdivided into p-type or trivalent and n-type or pentavalent. On the left, we have 3 electrons orbiting in the outermost shell of an atom. It is called trivalent. And on the other atom, we have 5 electrons and is called a pentavalent. Common examples of trivalents are boron, gallium, and indium, and those of pentavalent are phosphorus, arsenic, and antimony. The process of adding impurities to a semiconductor is called doping, and the impurities are called dopers. In case of trivalent, 3 electrons of boron will form 3 bonds with silicon, and as for the 4th electron of silicon, there will be a hole. As seen previously, the neighboring electrons will be attracted to the hole, creating another empty space in its previous location. Meanwhile, with sufficient energy, the normal electron-hole pairs are being formed throughout the silicon structure by breaking of the covalent bonds. Because of the additional holes created as a result of the impurity, overall there will be more holes than electrons. This is a p-type extrinsic semiconductor. The next type is an n-type extrinsic semiconductor. Here, the impurity atom will have 5 electrons in the outermost energy shell. But silicon requires only 4 electrons to complete its bonding. So we shall have an extra electron in the structure. So we get a net negative charge due to this extra electron, hence the name n-type. When we add a pentavalent impurity to an intrinsic semiconductor, we observe that the phosphorus atom forms 4 covalent bonds with the silicon atom, fulfilling the needs of silicon. But even after that, there remains 1 electron which does not form any bond and remains free. And so, unlike the previous structure, we get free electron available for conduction. This electron rotates randomly around the phosphorus atom, following a circular motion. In addition to this, the breaking of bonds as seen in intrinsic semiconductors happens here as well. The p-n junction. A p-n junction is an arrangement obtained when a p-type semiconductor is joined to an n-type semiconductor. This is a p-n junction. Immediately it is formed, the p region contains mobile holes and negatively charged impurity ions, which are fixed. The n region contains positively charged impurity ions, which are fixed, and mobile electrons. Many electronic devices use a p-n junction. As soon as the p-n junction is formed, electrons from the n-type material and holes from the p-type material diffuse into the opposite materials respectively. The electrons and holes diffusing towards each other combine near the junction. Each recombination eliminates a hole and an electron. As a result, the positive donor ions in the n region and the negative acceptor ions in the p region are left uncompensated. This forms the depletion region. This is named so because it is depleted of mobile charge carriers. The holes trying to enter the p region are repelled by the uncompensated positive charge on the donor ions, and the electrons trying to enter the n region are repelled by the uncompensated negative charge on the acceptor ions. As a result, potential difference is established across the junction. Soon it becomes large enough to prevent further movement of charge carriers. This is called potential barrier or junction barrier or height of the barrier. You can clearly see that the potential barrier VO that is set up gives rise to an electric field that prevents the respective majority carriers from crossing the barrier region. What will happen when the negative terminal of a battery is connected to the p-type region and the positive terminal to the n-type region? Observe if there is any deflection on the ammeter. As no current flows through the circuit, the ammeter reading is 0. This is because the electrons in the n-type region get attracted to the positive terminal of the battery, and the positive holes in the p-type side get attracted to the negative terminal of the battery. That is, the reverse bias removes the majority of carriers, thus increasing the potential barrier. What if connected as shown here? Holes and free electrons enter the depletion region due to repulsion at the respective terminals. The reduction of potential difference of this region causes a large number of charge carriers to diffuse across the junction. Holes travel to the right and electrons to the left, constituting a current in the same direction. Thus, the p-n junction allows current carriers to flow through it if the junction is forward biased. A device that allows current flow only in one direction is called a diode. Thus, a p-n junction can be described as a diode. Described as a diode. We now look at the current voltage characteristics of a p-n junction diode in forward and reverse bias. We have seen that a p-n junction diode is formed when a pure semiconductor is partly doped, such that the p side has holes as majority charge carriers and the n side has electrons as the majority charge carriers. In a forward bias, when a cell is connected across the diode, the n side of the semiconductor is connected to the negative of the cell, and p side is connected to the positive of the cell. Then, the barrier potential decreases, and due to the process of minority charge carrier injection, that is, the p side has holes and n side has electrons, produce a diffusion current which is measured using a milliammeter. In a reverse bias, when the cell is connected across the diode, the n side of the semiconductor is connected to the positive of the cell, and the p side is connected to the negative of the cell. Then, the thickness of the depletion layer increases. The diffusion current reduces enormously, but some of the holes on the p side and the electrons on the n side come close to the junction and are swept towards the majority zone. This is called drifting of the charge carriers. Thus, a drift current of small value is produced and is measured in microamperes. Displayed here is a p-n junction characteristic measurement apparatus. It consists of two DC power supplies, two voltmeters of range 0 to 1 volts and 0 to 20 volts, a 0 to 15 milliamperes milliammeter, a 0 to 100 microamperes microammeter, two p-n junction diodes mounted behind the panel. Observe that the left side of the circuit shows the p-n junction in forward bias, while the right side shows reverse bias. Let us now perform an experiment and see the characteristic of a p-n junction in forward and reverse bias. Connect the wires as shown. It might be necessary that you pause the video to see the connections clearly. For forward biasing, rotate the knob to increase voltage in steps of 0.05 volts. And note down the corresponding reading on the milliammeter. Record your observations. For reverse biasing, rotate the knob to increase the voltage in steps of 1 volts and note the corresponding reading on the microammeter. Record your observations. Let us plot the observations on a graph taking forward voltage along x-axis and forward current along the y-axis. Reverse voltage along negative x-axis and reverse current along negative y-axis. Observe that in forward biasing, the forward current initially remains zero till the barrier potential of the junction is reached. Thereafter, the current starts increasing slowly in the beginning and then rapidly. The value of forward bias voltage at which the forward current just starts increasing is called the cut-in voltage or threshold voltage or breakpoint voltage. Calculate the slope of resistance Rf in the upper portion of the graph where the value of voltage is less, the value of current is more, and the graph is steep. This value is generally less than 100 ohms and is referred to as the dynamic value of resistance in forward bias. As the voltage is increased from zero, a very small current flows through the diode because forward bias voltage is insufficient in opposing the potential barrier. Leakage current due to flow of minority charge carriers flows. When the potential barrier is completely overcome by the bias at the cut-in voltage, charges easily flow across the junction, giving rise to a sharp increase in forward current. In reverse biasing, when the reverse bias increases, there is a very small reverse current flow which remains almost constant, independent of the bias voltage. But when the reverse bias increases to a sufficiently high value, the reverse current suddenly increases to a large value. This voltage at which the reverse current increases sharply is called the breakdown or Zener voltage of the junction diode. Calculate the slope in the upper region of the graph where it takes a curve. Note that the value of the reverse bias resistance is of the order of 10 to power 6 ohms, as the diode offers more resistance in reverse bias. This value is also referred to as the dynamic value of resistance in reverse bias. And finally, we look at the application of junction diode in rectification. A rectifier is a device that is used in transforming an alternating voltage and current into a direct voltage and current. The process is called rectification. There are two types of rectification: half-wave rectification and full-wave rectification. Before we discuss how rectification is done, we need to understand two things: alternating voltage and current, and direct voltage and current. When the available voltage from an electrical source changes its direction periodically, it is called an alternating voltage, and the source is called an AC source. If we plot a waveform of an alternating voltage against time, we will see that the wave is sinusoidal in nature. This shows that voltage increases in one direction until it achieves a maximum positive amplitude. It then decreases to zero and then changes its polarity until it reaches a negative maximum amplitude and then reduces back to zero. If we apply an alternating voltage to a load, a current gets set up in the circuit. The flow of current follows the nature of the applied voltage, changing from one direction to the other. This changing current is called an alternating current. And now direct voltage and current. When the available voltage and current does not change its direction with respect to time, then it is called a direct voltage and current respectively. For example, the voltage available at the terminals of a cell and battery is direct voltage because it does not change its polarity and remains constant in magnitude. When this voltage is applied across a load, current will also be direct in nature, meaning that it does not change in direction and magnitude with respect to time. A semiconductor diode has two terminals, anode and cathode. We know that a diode only conducts current when it's forward biased. In this case, the diode offers very little resistance to current flow. We can say that it behaves like a closed switch. When reverse biased, the diode does not allow flow of current, and that is because the anode is at a low potential and the cathode at a high potential. In this case, the diode acts like an open switch. Half-wave rectification. When the available voltage is alternating, but the required one is direct voltage, conversion is done. It is called AC to DC conversion or simply rectification. The circuit used is called a rectifier. This is a half-wave rectifier. It consists of an AC supply, a step-down transformer, a diode, and a DC electric load, which is basically an electric device that runs on direct current, like a bulb. When the AC supply is switched on, the alternating voltage AB appears across the primary winding of the transformer. This voltage is reduced to a level suitable for the diode and the load on the secondary winding of the transformer. That is the voltage across CD or VCD. When this alternating voltage VCD is applied across the DC load, having a diode in series with it, what will happen? During the positive half cycle, the terminal C is positive and D is negative. Under this condition, the diode is forward biased because the anode is at a higher potential with respect to the cathode. So the diode behaves like a closed switch, allowing a current to flow through the load. The current varies in magnitude as shown here, just like the voltage. During a negative half cycle, the terminal C is negative and D becomes positive, and hence the diode is reverse biased. It therefore does not conduct and no current flows through the circuit. Thus, during the negative half cycle, no voltage appears across the load. And then we make into another positive half cycle when the current flows. These positive and negative half cycles will continue unless the load is disconnected. And so from these graphs, we notice that the input voltage has both the positive and negative values. It is alternating. The output voltage and current only have the positive values, and so the diode cancels out the negative values. The plateau section tells us that the output is not a continuous direct current but a pulsating DC wave. Since only half the cycles of the output wave are used, it is called a half-wave rectifier. Now full-wave rectification. Full-wave rectification is divided into two: full-wave bridge rectifier and full-wave rectifier with center-tapped transformer. The difference is in the elements used. Full-wave bridge rectifier. Full-wave means that the rectification happens in both the negative and positive cycles. The setup used is similar to a Wheatstone bridge. It consists of an AC supply, a step-down transformer, 4 diodes D1, D2, D3 and D4, and a DC load which could be a bulb. When the AC supply is switched on, the alternating voltage VAB appears across the primary winding of the transformer. This high voltage VAB is reduced to a level suitable for the diode and the load on the secondary winding. VCD is the voltage across point C and D. During the positive half cycle, the terminal C is positive and the terminal D is negative. Under these conditions, the diodes D2 and D4 are forward biased. They thus behave like closed switches. Therefore, current flows through the load through this path during the positive half cycle in the direction A to B. This current varies in magnitude as shown on the graph. During the negative half cycle, the terminal C is negative and terminal D becomes positive. Therefore, diodes D1 and D3 are forward biased, while diodes D2 and D4 are reverse biased. So the current follows this path and again from A to B across the load. Therefore, during both parts of this cycle, current across the load flows in the same direction, A to B. On the graph, there are no plateaus. This cycle will continue until any component is disconnected. This way, the bidirectional alternating current gets converted to a unidirectional direct current. And finally, the center tap full wave rectifier. And so for a bridge full wave rectification, we require 4 diodes. Full wave rectification can also be done using only 2 diodes when we use a center tapped transformer. These diodes D1 and D2 are connected to the opposite ends of a transformer. The center tap is usually considered a ground point or the zero voltage reference. When we apply an AC input to the primary side of the transformer, this input makes the secondary ends S1 and S2 become positive and negative alternately. For the positive half of the signal, the secondary terminal S1 is positive. Ground point will have 0 volts and S2 will be negative. At this point, diode D1 will be forward biased and D2 will be reverse biased. So D1 conducts, but D2 does not. The current thus flows in this direction. We call it A to B, and a voltage drop will appear across the load. During the negative half cycle, the secondary terminal S1 becomes negative and S2 becomes positive. At this point, D2 is forward biased and D1 is reverse biased. D2 will conduct, but D1 will not. The current flow will be in this direction, again A to B, and voltage drop will appear across the load. So you see the current flow across the load is in the same direction in both cycles. Thus, a full wave rectification is accomplished using this center tap transformer and 2 diodes.
The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment Els Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course, this was electrical energy. Now, you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cornelius at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful, and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.